Hey guys, today we're going to be talking about Bohr models. That's named after Niels Bohr, the guy who made the Bohr model, Bohr models and valence electrons. So settle in, get ready to go. All right, first things first is going to be Bohr models. So you may remember that we talked about how Bohr said there was a nucleus made up of protons and neutrons, but people had said that before him. What he came up with was the electron levels that go around an atom. And we've been looking at electron configurations and where those electrons live on these rings. And we said that each ring has a number called the principal quantum number. That's just the number of rings out it is from the center. And so far, what we have discovered is we know elements that go up to 7 rings. There could be more than that if we discover more elements. So you could, have some conditions where there could be more, but we really only know up to 7. So we want to be able to discuss how many electrons are on each level, and we do that by drawing a diagram. Now, drawing a Bohr diagram or a Bohr model like this with these concentric circles where you have to draw giant circles is really tedious and annoying, and nobody wants to do it. So we have kind of a shorthand way that we might do that. Now, the idea and the structure kind of remains the same. So you've got a nucleus, and this first line, I'm actually going to make it blue, is going to be the nucleus. And inside the nucleus, you have some number of protons and some number of neutrons. So whatever atom you're looking at, you'll write down number of protons, number of neutrons. You have to figure that out. And then going on the outside are rings. And for each ring, you'll put the number of electrons that reside on that ring. The first ring can hold up to 2, the second ring can hold up to 8, the third one can hold up to 18, and a fourth one after that, and any following the fourth one can hold up to 32. So to write your Bohr model, you just have to draw these things and put in numbers for each position. For my example here, I'm going to use the element indium, which is In, indium, and it's going to have a mass number of 113, which I think is one of the, if not the only, stable isotope of indium. And if you go find it on the periodic table, you'll see it has an atomic number of 49. So this is the isotopic notation for indium. And we're going to draw the Bohr model using the isotopic notation. And we're also going to have to know the electron configuration for indium. The electron configuration for indium is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2. I'm going to have to make it a little bit smaller to keep writing. I'll just scoot it over a little bit. 5s2, 4d10, and 5p1. Now, hopefully you already know how to find those, and you're going to have to know how to find electron configuration in order to do the Bohr model correctly. So I highly recommend, if you don't know how to do this, stop now, go learn how to do electron configuration from a previous video, and then come back to the Bohr model, because you have to know this electron configuration and what it means in order to do the Bohr model correctly. Now we're actually going to draw the Bohr model. We're going to start with the nucleus. So this is going to be my nucleus. And in the nucleus, I'm going to have some number of protons. The number of protons comes from your atomic number, which for indium is 49. We have 49 protons. And then we got to find neutrons also to go in the middle. So neutrons, you can find neutrons equals from the mass number and the number of protons. Neutrons equals mass number minus protons. Our mass number is that number up on top, of the isotopic notation. So you do 113 minus 49 to get your answer, which is 64 neutrons. So we got 49 protons, 64 neutrons in the nucleus. The thing that's left to figure out is the number of electrons on each ring going away from the nucleus. And you can tell where the electrons are from the handy-dandy electron configuration. Each coefficient here, the coefficients are the big numbers that are in front of the letters, so these things. These tell us the level that the electrons are residing on. And I'm going to go ahead and color code them by level. Level 1 is yellow. Level 2, I'm going to make green. Level 3 is going to be blue. Note that there are 3 different 3s. They're split apart. And then level 4, same thing. There's 3 sets of level 4s. They're spread apart. And level 5. Okay. So now I'm going to take the electrons from each of those levels and write them down in the Bohr model. On level 1, which I'll draw here, we're only looking at the electrons with the yellow highlight. So level 1 only has the s orbital, and in the s orbital, there are 2 electrons total. So level 1 only has 2 electrons, which is good because level 1 can only hold 2 electrons. We move up to the second level. Second level, things are highlighted here in green. And there's 2 orbitals on the second level, s and p. If you take the s and the p and add them together, you get 2 plus 6 is 8 electrons. The next orbital, the next ring is the third level. We got 3 of those, the s, p, and the d. We have to add those all up. 6 plus 2 is 8, plus 10 is 18 electrons for my third ring. For the fourth ring, we again have 3 sets, s, p, and d. So we do 2 plus 6 is 8, plus 10 is 18 electrons. And lastly is the fifth level. Draw that there. Lastly is the fifth level, which only has s and p. It's got 2 on the s and 1 on the p for a total of 3 electrons for that fifth level. Sorry, my drawing got a little squished. We will live. So that's the whole Bohr model. You've got a nucleus with protons and neutrons, and you've got all the electrons residing on the outside. All right, so we're going to take a look at a couple of things from this Bohr model. I've redrawn it conveniently for you here, but so that I have more space. And the thing we need to look at today is the valence electrons. That's valence, V-A-L-E-N-C-E. This means the outer electrons, which are the ones on the outermost ring. So here on this diagram, that's this ring, and there's 3 electrons there. So indium has 3 valence electrons. To find the number of valence electrons, you just go look at that last shell on the Bohr model. And electrons, or valence electrons, are super important because they define the way that the element behaves. All the other electrons are way less important. It's the valence electrons that count. And we're going to learn to draw a diagram about the valence electrons called a Lewis dot diagram. Lewis dot diagram. Pre-AP kids, you will be using these extensively when it comes to bonding. On-level kids, you still need to know them, but we won't use them quite as much. So a Lewis dot diagram takes the valence electrons and places them around the symbol. So we're doing indium here. Indium is In. And the way that the Lewis dot diagram works is that it fills up spaces around the symbol according to the way it would fill up orbitals. So we know that in orbitals, if we have the little s orbital and we have the p orbital, it fills up the s first and then goes over and fills up the p, and it spreads out in the p before going to fill back in. Lewis dot diagrams work the same way. we put the s orbital over on the right and the p orbital everywhere else around. And as we fill in valence electrons, we'll fill in that same order. So indium has 3 valence electrons. I'm going to make them red. So it's going to fill in the 2 spots in the s orbital first, because each of these spots has 2 spaces, just like in the orbital notation. So the s side has 2 spots and we fill them first. And then after that, we move to the p orbital. Now the rule is that we go counterclockwise. So from the s, we'll go to the p, and the p's will continue around that way. So we've got 2 electrons already in. Our 3rd electron is going to go up to p. Now, if this was an element that had more valence electrons, that more than 3, if this wasn't indium, you would continue filling in this manner. You would go to the next p, because they like to spread out in the p orbital. Go to the other one after that, and then start filling back in around on the p. So the order you fill them in looks like 1, 2, 3, 4, 5, 6, 7, 8, for a total of only 8 possible valence electrons. And then we can use diagrams like the Lewis dot diagram, say for indium, which looks like this, to find oxidation numbers for elements. And the reason we have to do this is because of something called the octet rule. We know that oct means 8, and the octet rule says that all atoms want 8 valence electrons. All atoms want 8 valence electrons. And there's a little bit of a caveat to this. It's they either want 8 valence electrons or they want to lose their valence electrons. And we'll see what that means here in a second after I get done writing it. So we've got indium here. It's got 3 valence electrons and it wants 8. So I'm going to draw empty spots for all of its extras that it wants. It's got 3. It needs to go find 5. Now, it's going to be a lot harder for indium to find 5 electrons than to find places for 3 of its electrons to go. So instead of finding a bunch of other electrons, indium's going to get rid of its electrons. That means it had 3 extra electrons. It's getting rid of those negatives. So it's going to end up with an overall positive charge of 3. Because it was initially neutral, is losing 3 negatives, which makes it a positive 3. So in order to fulfill the octet rule, indium's going to try to get rid of those 3 electrons, giving it an overall charge of positive 3. Now let's look at this again with some other examples just to try to, figure it out. Let's take a look at fluorine, for example. Fluorine has 7 valence electrons, which you could figure out using the Bohr diagram, or the Bohr model. And they go in order 1, 2, 3, 4, 5, 6, 7 valence electrons, and it's missing 1. Now it's going to be way easier for fluorine to find 1 measly electron than to get rid of all 7 of its others, because when it gets rid of those electrons, it has to find places for them to go. And so fluorine is going to steal an electron from somewhere else. And when it steals an electron, it becomes slightly negatively charged, making it a -1 charge. So fluorine becomes slightly negatively charged. These numbers, the things that they become charged to due to the octet rule, are called oxidation numbers. And they are the same for everything in a group, which you can see if you draw the Lewis dot diagrams for all of the different elements in a group. Now, last little bit of vocabulary before I let you go is cation versus anion. Well, in ions in general. So an ion is defined as an atom that gains or loses electrons. Gains or loses electrons. So, for example, indium, here, it lost 3 electrons, got rid of them, and became positive. Fluorine became negative when it gained an electron. So these are both ions. One that is positively charged is called a cation. One that is negatively charged is called an anion. And you can remember this because you think cats are positive, but onions are negative in some people's opinion, not mine. But that's what my classes came up with. What I used to think of it as was ants are negative. So cations are positive, ants are negative. That was a real quick, real brief overview of Bohr model and Lewis dot diagram and octet rule, which is a lot of heavy stuff. So if you have questions, please look over the slides, but also you can email me or Miss Rigsby or Coach Sharp, or you can look up some videos on YouTube that are instructional and helpful. Whatever floats your boat, whatever you need to do. But please, if you're lost on something, get help.